Alright, welcome to this video where we're going to talk about the atomic mass that is found on the periodic table. So before we get started, I want you to go ahead and take a look at this symbol, and remember the top number tells us the atomic number, which is the number of protons. Then we have the symbol, the name, and then we have the atomic mass. And we haven't really talked about that, but now we are going to get into that. What I want to really emphasize is that the atomic mass is different from the mass number. The mass number of an atom is the protons plus the neutrons. And so if you add the protons and neutrons together, you get the mass number. Now the atomic mass, however, is an average of all the different isotopes. So to give you an example, let's say that we have 10 people. And let's say 8 of those people are 200 pounds, and then 2 of those people is 150 pounds. What would the average be? Well, the average would be something that is close to 200 because you have more people that weigh 200 pounds. However, what if we had 10 people and 2 of them were 200 pounds and then the other 8 were 150 pounds? Well, then that average would actually be closer to 150 because it's the most abundant not isotope, but most abundant weight. Now, let's compare that to isotopes. Now, silicon has several different isotopes, and if you take a look, the average atomic mass is 28.086. What that means is that the most abundant isotope is probably silicon-28. However, there's probably, there's a certain amount of silicon-29, and so that makes the average not exactly 28. And so again, that is a weighted average. We're going to talk about how to calculate that, and we're going to talk about how we even determine the weights of these atoms. And so the average atomic mass is the weighted average mass of all the elements isotopes, or of the isotopes of an element, and it is the mass found on the periodic table. So again, it's a weighted average. Now if you take a look, there's an equation on the bottom there. I don't want you to really look at that equation too much. I would rather you go to the guided practice problem video and see how I calculate it, because it's actually really easy. But let's go ahead and move on here. So again, it's the atomic mass on the periodic table. It's an average of all of the different isotopes. The average atomic mass will fall between the mass of the smallest and largest isotope. And so to give you an example, let's go back to my example where we have a bunch of people that are either 200 pounds or 150 pounds. Now, no matter how many of each we have, if we only have people that are either 200 or 150, that means the average cannot be greater than 200. It also means that the average cannot be less than 150. Because again, it's got to be somewhere in the middle of the smallest and the largest. So if we have, for example, carbon-12, carbon-13, and carbon-14, that's a mass of 12, 13, and 14, that means that the average has to be somewhere between 12 and 14. It can't be less than 12, and it can't be greater than 14. It has to be between the smallest and the largest. Now, the average atomic mass will generally be closest to the most abundant isotope. For example, carbon-12 happens to be the most abundant isotope of carbon, and if you look at the average atomic mass on the periodic table, it happens to be 12.01. And so that is an example of how the average atomic mass will generally be closest to the most abundant. And so if we think about, let's say we have boron-10 and boron-11, if 90% of all boron atoms are boron-11 and 10% are boron-10, that means the average is going to be closer to boron-11. Now, the masses of elements and their percent abundance of isotopes of elements are measured using mass spectrometry, which is a technique that separates particles based off of their mass. And so what I'm going to do is I'm going to show you a mass spectrometer, and I'm going to explain how it works, but you don't necessarily need to know how it works. but I am going to explain it so that you can understand what it is. And so this happens to be a mass spectrometer. And if you take a look, if we have, let's say, carbon 12, 13, and 14, we have a sample of carbon, and we have some carbon 12, some carbon 13, and some carbon 14, what we can do is we can shoot it down a tube where it is ionized, and we'll talk about what it means to be ionized in the future unit. But essentially what that does is it makes it a charged particle. When you ionize it, it becomes a charged particle. And as it shoots down, what will happen is it'll pass through a magnet, and because it's a charged particle, the magnet causes it to bend. Now I want you to think about a shopping cart. Think about a shopping cart that's full of food and a shopping cart that's not full of food. If you were to push the shopping cart that is not full of food, it will move faster than a shopping cart that is full of food because there's more mass. And so the same concept is true here. When these particles are passing through the magnet, the lighter particles will actually get pushed more, so they'll bend more. The heavier particles will bend less. And notice the last part of the mass spectrometer. You'll see that the heavier particles, because they're not bend as much, are all located in one spot, and then the lighter particles are located in another. And so this essentially is separating the heavier particles from the lighter particles. So again, if we had carbon 12, 13, and 14, the carbon 12 would be bent more, so the path of it would be bent more. The carbon 14, the path would be bent less. Now again, the way this works doesn't matter. I just explained it so you can understand this next part. What this then does is the ionized material is separated according to their mass, and the result of which produces what is called a mass spectrum. And the way the mass spectrum works is that whichever isotope is the most abundant, the sensor will say that is 100%. And then what it does is it records the other isotope as a percentage of the one of the greatest abundant. And so I'm going to show you an example of this in just a moment here. And so the position of each peak on the x-axis indicates the mass of the isotope that was ionized. So for example, the yellow peak there, this happens to be for silver. The yellow peak happens to be for the mass of silver, that is 107, and the blue peak happens to be for the mass of silver, that's 109. And so let me go ahead and I want to talk about how we get that 100% and how we get the other one. So let's go ahead and say we have element X. And let's say that we take element X and we put it through the mass spectrometer, and let's say that there's 80 atoms of element X, of X15, and so it's whatever element X is that has a mass of 15, and then there's 20 atoms of element X17. And so what will happen is the mass spectrometer will say that 80 atoms, which is the most abundant, is 100%. And then what it will do is it'll say what is the percentage of that 20 compared to that 100%. And so 20 happens to be 25% of 80. And so notice how the mass spectrometer would end up giving us a mass spectrum where the X15 will have 100%, and then the X17 will have 25%, because it shows how much or what the abundance of 17 is in comparison to the 15. And so what you then need to do then is when you have this this mass spectrum here, you need to normalize it. In other words, when you see the intensity here, where for example the 107 is 100%, that doesn't mean that the percent abundance is 100%, because if you have a bunch of different isotopes, each isotope is going to have its own percentage, and all of those percentages have to add up to 100. So the fact that one of them is already 100 doesn't even make sense. And the reason why it is 100 is because it's not saying that the percent abundance is 100, it's saying that that is the most abundant isotope. And so what we're going to do here is, again, it's going to be really important to look at the guided practice problems and follow along with the guided practice problems for this particular set of notes, because we're going to talk about how to calculate average atomic mass, and then we're going to talk about how to normalize these mass spectrums. And so again, we'll talk about that in the guided practice, so it's going to be very important. And if you have any questions after the guided practice, go ahead and email me. I know that this is a lot going on here, but it's really not that bad once you understand the math behind it. So you guys have a great day, and take care.